Every day, we make and use all kinds of measurements, from looking at our watch to reading the speedometer in our car. The figures on our utility bills, the amount of active ingredient in our medicine, and the wind speed in the weather forecast are all the outputs of measuring systems. Some everyday measurements are very accurate and some aren't. Even the cheapest digital watches are accurate to a few seconds a year, while a domestic oven thermometer can be wrong by several degrees. The situation has evolved because the accuracy you need to not miss an appointment is not the same as it is to bake a cake. As we will see, making measurements that are only as accurate as it needs to be is important for many applications. The need for the establishment of scientific standards and the production of interchangeable parts in manufacturing has historically driven the need for ever more accurate measurements. When cars and other machines were first built, exact measurements didn't matter. Each part was custom made to fit with the parts that were already there. This led to cars and other machines being incredibly expensive to build and maintain, which led to Henry Ford and others to develop mass production of standardized parts. Today, more than 80% of components used by any manufacturer are made by other companies all over the world. Every manufacturer needs to tell its subcontractors the range of acceptable values of dimensions, electrical characteristics, and other parameters of all these components. Otherwise, the devices won't work or fit together. Accurate measurements ensure that standards can be used to make technology run as smooth as possible. We expect our appliances to work when we plug them into any outlet. Our smart cards will swipe any reader, and our devices to connect with any open Wi-Fi network. Standards organizations such as ISO and IEEE maintain these standards to enable the easier development of technologies and greater choice for customers. The science of measurement is known as metrology and can be divided into scientific, industrial, and legal metrology. Scientific metrology aims to develop and provide international measurement standards. Industrial metrology is the application of measurement science to industrial processes, and legal metrology underpins fair trade and consumer protection. To make any kind of measurement, you'll need to use a reference, such as measuring a piece of wood with a tape measure. Without any reference, no measurement can occur. If you found that one of your shoelaces is longer than the other by comparing them side by side, that is not a measurement. If you use a ruler to find out the difference in length, this is a measurement. If you want to compare the measurement with someone else's, you will find it a lot easier if you can agree on using the same units. In the past, units were defined by a country's ruler, which gave us imperial units. In order to establish and maintain an international standard, internationally agreed references have been produced, most notably the SI system of units. These references are kept by the International Bureau for Measures in Paris, but these references are not static. For example, the international standard for the kilogram is a bar of metal, kept in a vacuum at a fixed temperature. Despite the care in which it is maintained, it is constantly changing. Atoms are constantly falling off, getting stuck to it, or disintegrating inside it because atomic decay occurs in every material. The corresponding changes in mass are tiny, a few micrograms per century, but this means that the kilogram bar cannot do its job indefinitely. So by that rationale, no measurement is, or ever can be, exactly right. This is really no cause for alarm, as none of us really need measurements to be exactly right. We only need the measurement to be as accurate as we need, or in other words, what uncertainty we can tolerate. If we only need the measurement to be to the nearest centimetre, we can say that measurement is not to get the right answer, but to decide on the uncertainty that can be tolerated. One problem is defining exactly what these measurement terms mean, and another is that some measurements only make sense when several measurements of the same thing are made. That's because making a good measurement is much like trying to hit a target. The chances of getting a satisfactory result is greatly increased if you make several attempts. A good measurement result is achievable by using 1. The right measurements. The role of the measurement is known in the process, and its use is clearly defined and understood to identify potential problems and improvements. 2. The right tools. The measuring instruments need to be in a good state of repair and calibrated. They also need to be used according to the manufacturer's recommendations. 3. The right people. Whoever makes the measurement needs to have received the right instructions and training. 4. Regular review. Measuring instruments are easily damaged and their performance changes over time, so regular checks are required. A planned written schedule of checks is beneficial to avoid delays. 5. Consistency. Local factors need to be taken into account, particularly with highly accurate measurements. Gravitational forces and temperature are variables that can alter a measurement. Multiple measurements may need to be taken in order to make corrections or carry out further investigations. 6. The right procedures. Measurements should be carried out according to written procedures, which may include health and safety issues. A risk assessment may also be part of the procedure for measurement. Here are a few terms used in measurement and what they mean. Confidence level and uncertainty. If you make a number of measurements of something, you are most likely to get a range of answers. If you find that the concentration of carbon monoxide gas in your area lies between 9 and 11 parts per million, but you couldn't be 100% sure that it is, you could express your confidence through statistical analysis that you are 95% confident that it lies between those values. Uncertainty is the doubt that exists about the result of any measurement. Since there is always a margin of doubt about any measurement, we need to know the size of the margin and the size of the doubt to know the uncertainty. We might say that the length of a pipe measures 10 centimetres plus or minus 1 centimetre at the 95% confidence level. This result could be written 10 centimetres plus or minus 1 centimetre at a level of confidence of 95%. This says that we are 95% sure that the pipe is between 9 centimetres and 11 centimetres long. Error simply refers to the difference between the measured value and the true one. A tolerance is the maximum acceptable difference between the actual value and the value specified for it. For example, if a 10 ohm resistor has a tolerance of plus or minus 10%, the minimum acceptable resistance would be 9 ohms and the maximum would be 11 ohms. Precision and accuracy. If you make several measurements and find they also agree closely with each other, then they are precise. If they agree closely with the actual value, then they are accurate. Trueness and bias. Trueness is the closeness of a measurement to the average of a large set of measurements. Bias is like the opposite of trueness. It occurs when the measurement indicated is consistently too high or too low. This may be because of an inappropriate measurement method. Repeatability and hysteresis. Repeatability is the measurement indicated by an instrument under the same conditions, using the same equipment in the same way. Repeatability does not guarantee accuracy. Hysteresis is the amount of difference between the measurement of the same variable approached from different directions, i.e. a rising and a falling output. Excessive hysteresis will result in linearization error. An instrument's datasheet will specify the repeatability and hysteresis of an instrument as a percentage of the span. Traceability. All measurements need to be traceable through an unbroken chain of comparisons. Traceability is ensured by routinely calibrating to a higher level reference standard. Typically, we use a reference standard to calibrate our process instruments. These references are then sent periodically to a standards lab, which has more accurate instruments. The standards from the calibration lab are periodically checked against higher level standards, such as the national standards, which in Australia are maintained by the National Association of Testing Authorities. The national standards are ultimately referenced against the international standards. Factors affecting measurement. 1. The instruments. Electrical measuring instruments can be affected by electrical noise, either as background EMF or as a voltage disturbance. Proper earthing of equipment is also important, which can be tricky when several electrical instruments are involved in the same measurement. Common earths need to be set up and checked to avoid earth loops. 2. The variable. The measured variable may be a moving target, but the changes may be small enough to be disregarded. It may be the case that the variation itself is being measured. 3. Sampling, etc. The number of samples needed to reflect the reality of the process on the ground. If the measurements are not made in sufficient numbers at the appropriate positions and times, they will not be representative. 4. Operator skill. What is a possible level of accuracy for one person may not be achievable for another. As skills and experience vary, often setting up the measurement is more challenging than the measurement itself. 5. Environmental factors. Vibration, temperature, air pressure, and humidity can affect all types of measurements. Measuring a variable like gas analysis can result in samples being contaminated on the way to and in the lab, whereas inline testing will give a different result.